Welcome back. Advanced Convection, Part 2, Solution to Governing Equations. Topic 4, Introduction. In this section, we want to review the basic concepts and variables to lay out a solid foundation for further study. A. Let's review governing equations covered in Part 1, which is mass conservation, momentum conservation, and energy conservation. Each conservation has its own equation name: the continuity equation, the Navier-Stokes equation, and the enthalpy equations, because we have mechanical energy equation and kinematic energy equation. There are two questions related to the governing equations. Number 1, do they have unique solutions? The answer is yes, because we have 5 equations for 5 unknowns: 3 velocity, pressure, and temperature. Number 2, why are they called governing equations? This is because all the experimental evidence indicates that these equations are truly fundamental, and they indeed dictate any situation involving the flow of Newtonian fluid. However, this embracing all quality and the nonlinear term make the equations very difficult to solve. Sometimes it is impossible. Then do we have hope to find solution? Sure. B. Then what are the strategies of finding the solution to those very difficult governing equations? Generally speaking, there are 2 categories. One is to seek exact solutions for very simple flow and geometries. 2 is to make realistic assumptions to obtain approximate solutions. For example, for fully developed internal flow, the exact solutions to the governing equation do exist. At this point, you may wonder, it appears that we are kind of obsessed with the exact solutions, but why? The reason is that the exact solutions play a very critical role in proving or disproving the laws, assumptions, and verifying numerical simulation and even experimental results. On the other hand, for approximate solution, it really depends upon the Reynolds number. For very high Reynolds number, we can separate or couple the boundary layer flow and inviscid flow to simplify the governing equations. For very low Reynolds number, the flow is called creeping or Stokes flow. It is always laminar and the viscous force dominates. This can be used to simplify the governing equation to get approximate solution. However, for a turbulent flow or very highly advanced problems like a weather prediction, we have no choice but turn to CFD, the computational fluid dynamics, for numerical simulation. C. Now, we will review the hydrodynamically fully developed flows. As you have seen, when the flow enters a pipe or channel, there are two flow regions in terms of entrance region and fully developed region. The flow pressure is changing over the flow direction, and the pressure drop is linear in the fully developed region. But the question is, what is a hydrodynamically fully developed flow? It is defined as flow is fully developed hydrodynamically when the velocity profile for a fluid that does not change along the flow direction. There are three mathematical implications associated with the definition. First, since the velocity profile does not change over the flow direction, there is no acceleration. Therefore, the velocity in the flow direction, x, is only a function of y over r. Second, from the continuity equation with the no acceleration condition, we can demonstrate the velocity in the y or r direction is 0. Third, since there's no acceleration, the force is balanced. Therefore, the pressure derivative in the flow direction x is constant. D. Next, let's examine a few representative fully developed flow hydrodynamically. First, this is momentum conservation or Navier-Stokes equations. The flow is subject to pressure force, viscous force, and gravity. Second, for a channel flow or a pipe flow, it is a pressure driven, which is the pressure force overcomes the viscous force to push the flow moving forward. And the pressure derivative in the flow direction x is constant. For a plain co-ed flow, it is shear driven, that is, the viscous force or the friction is the sole force to carry the flow moving forward, and the flow pressure in the flow direction doesn't change. Third, for the falling film, like falling water down an inclined plate, the flow is purely driven by the gravity to overcome the resistance, viscous force. From these three examples, it indicates that some forces are dominant, others are disappeared. E. Now, let's review thermally fully developed flows. Unlike velocity, the flow temperature and mean flow temperature never reach constant values along the flow direction, which is mathematically represented in equation 2. Instead, for thermally fully developed flows, the temperature difference ratio doesn't change over the flow direction, or it reaches constant. Furthermore, for thermally fully developed co-ed flow with constant surface temperature boundary condition, there is no change of flow temperature in x direction. That is, the flow temperature only a function of y. For a thermally fully developed channel or pipe flow with constant heat flux boundary condition, the temperature derivative in the flow direction x is a constant, but not zero. For thermally fully developed channel or pipe flow with constant surface temperature boundary condition, the flow temperature derivative in the flow direction is not a constant. This is the mathematical indication for thermally fully developed flows. F. There are more implications for the thermally fully developed flows. This represents the internal flow entrance region, a fully developed region, and this represents the heat transfer coefficient varies over the flow direction. From the definition of thermally fully developed flow condition, we can demonstrate that the heat transfer coefficient and the Newton's number are constant in the fully developed region. It doesn't matter whether it is laminar flow or turbulent flow. Keep this in mind. Finally, let's review the definition for the mean velocity and mean flow temperature. This is the pipe flow with velocity distribution, pipe flow with the temperature profile, and this is the channel flow. This is the cross-section area with either velocity or temperature profile. First, the mass flow rate m dot is defined as density times mean velocity times cross-section area. From the definition of mass flow rate, we can define the mean velocity, um, and it can be calculated from the integral of velocity profile over the cross-section area divided by the area of the cross-section. Second, the enthalpy rate h dot is defined as mass flow rate times specific heat times mean flow temperature. from this definition, we can define the mean flow temperature Tm. And it is calculated from integral of product velocity and temperature profiles over the cross-section area and divided by the mass flow rate. At this point, we covered topic 4. After this section, you're expected to know both plane co-ed flow and pipe channel flow in terms of its driven force, its characteristics, and the mathematical implications for hydrodynamically and thermally fully developed flows, as well as how to find the mean flow temperature Tm. See you next time.